We're on to chapter 9. So this is the second part of the physics component of this course, and we're referring to stresses. So what is a stress? Well, let's talk about chapter 8 in terms of where it's located in terms of structures. So chapter 8 was on forces. Remember, it was all the forces we talked about. So chapter 8, here's an object, here's a column, and it's under some forces. See, the forces are over here. Those forces are on the outside. So forces are external to the structure. Stresses is on the inside. Thank you. Thank you, Shalon. Stresses are the phenomena that occur on the inside. So the question that you need to figure out how to answer is, how does this force here and this force here, how is that information transmitted? How is it transmitted on the inside? What's going on? Like, I don't understand how that's happening here. Like, this force is going up, and does it go through the material? You know, what is the phenomenon that's going on the inside? So the document here, it spends about 10 pages in very, very clear detail, walking you through step by step how the forces are transmitted through the object, through the material. The idea is that you can think of it, and again, very well written document. You can see that there are detailed diagrams explaining what's called a flow of internal forces. So this idea of having a flow of internal forces is really is kind of a bulk behavior inside the material. If you're trying to kind of get a better sense of what's happening here, this material is made of molecules, and those molecules have forces that are in between each other called intermolecular forces. So when you pull on something, the material itself has these intermolecular forces which resists the pulling because the molecules themselves are attracted to each other. So if you're pulling on something, the molecules will pull back to each other because they're attracted to each other. Conversely, if you push on something, the molecules will act like springs and they will resist back. So you can have a situation here like in compression where inside you're squeezing, so that means that the information, the material on the inside is pushing back. You can think of the forces that are going through the material like a little highway. So you can see here this visual here of forces like a little highway going through, flowing through the material. One thing that's very often confused is the direction of forces for compression and tension. So here's an object that is under tension. So are there any questions about what I mean by tension? What does it mean to say tension? Let me know in the chat there. What does tension mean? So what do you think tension is? Like what direction does tension act? Okay, you're using good keywords. Let me ask it a little bit more plain. Expansion. Thank you, Ram. Tension causes expansion. That's what I'm looking for, okay? So tension is a pulling on the outside. So it's a pull on the outside. Of course, my highlighting tool is not working here. So tension is a pull on the outside. And conversely, compression is a push on the outside, resulting in contraction. So we need to differentiate the two because it's interesting that the direction of the response on the inside for many people is counterintuitive. And we will discuss how that pushing and pulling on the exterior behaves. So far, I've written out two keywords. One is tension, one is compression, and then there's another type which is called shear. And I'll talk about shear in a second. Now, have you heard of tension, compression, and or shear in any other courses so far in your program? Has any teacher mentioned tension, compression, and shear? Which course was it? Which course was it? Okay, so not the shear one. Okay. Oh, in architecture. I gotcha. Okay, cool. So the difference between tension, compression, and shear, well, we have the difference between tension and compression, which is that tension and compression are on the outside, pushing and pulling. Shear has this interesting behavior, and I'll explain it this way. Take a look at these forces here. You see how the forces line up? You see that, how they line up? That thing there? That line segment is called a line of action. That's a line of action. So a line of action is the direction along which the forces act. Now, in terms of tension and compression, the line of action goes through all the forces. See, the forces line up beautifully. Same with compression. If you draw a line of action, what the heck was that? No, I'm not trying to sell a YouTube channel here. I was trying to okay, that's funny. I have to retype that. Excuse me. I might have to close and open PowerPoint because I'm trying to copy and paste and it's not retaining my copy command correctly. So anyway, that's the line of action that I'm going to draw in a second. That was very strange. Let's see here. So here's the line of action right through the material and in line with the forces. Shear is when you don't have a line of action that coincides with all the forces. You see here, this is a beam. We have a beam here, and here are the forces that are acting on the beam. Now, we're not going to get into analysis of external forces on beams. If you're interested in seeing how to do analysis for beams, you're more than welcome to observe the other course, the Math 1181 course that I was mentioning at the beginning today, because I am going to do videos on how to analyze beams and trusses. So if that's something that you'd like to find out how to do the mathematics for, you can definitely watch those lessons as I post them over the next 2 weeks. But they're not for this course. So for this course, if you have a 1,000-pound force acting mid-span on a beam, we assume through symmetry, or we conclude through symmetry, that the reaction forces are 500 pounds each. And here's the thing. This force has a line of action here, that one has one there, and that one has one there. You see that those lines of action? Oh, Shalon, you're a champ. So that's exactly what it is, see? When the lines of action, I'll say it like this, when the forces do not share a single line of action, the object will bend. Don't worry, I'll clean that up in a second. Gotta squeeze it in here a little bit. So that's why beams bend. So this is the third type of situation. So we have something called tension, we have something called compression, and then in this case, when you have bending, bending will result in the shearing of the material. So now you have the kind of the summary of the three types of stress. You have the tension, which will result in tensile stress. You have compression, which results in compressive stress. And you have shearing, which is what's going to happen here. And I'll explain shear a lot better soon as we go through more of these pages. I will give you a definition of shearing. Shearing is the third type of stress, or the third type of stress that we're going to investigate. So here's stress. So we're on to kind of the next little topic here, which is the definition, or the concept, I should say, of stress. So as you go through this document, and again, I'm just kind of giving you the casual summary for some of these things. I do want you to read over this again on your own in patient detail, but I'll just give you an example of the units. Now, whenever I learn something in physics, there's formulas, but there's also units. So here's an example of units for stress, right there. So what does that stand for? What does this stand for? Let me zoom in there. Whoops. We have here LB, and then we have inches squared. What is that? What does that mean? Pounds per square inch. Thank you. So this is actually getting to a more formal definition of what stress is. Stress depends on how much force you have, and it depends on the area over which the force is distributed. So let me say that here. I like how I said that, and I want to paraphrase the author here. So stress, it depends on. So as I annotate these notes, you can kind of get an idea of what are really the key takeaways here. So you might say to yourself, like when I write here 590 psi, 590 pounds per square inch, what does that mean to you? Well, for me, let me say it like this. Will it hurt you? Will 590 psi hurt you? Think of that. Oh, put your hand on the desk, on your desk, and look at your thumb, okay? Just half of your thumb. I'd say that the average thumb, the half the thumb would be about a square inch, maybe 2 square inches, okay? Imagine 500 pounds sitting on the tip of your thumb. Would that hurt? Would that hurt you? Of course it would hurt you. I'd be freaking out, right? That'd be, well, I don't know. I don't know. You must be from Krypton or something. You must be like a superhero. Okay. But in all fact here, come on, 590 pounds over 1 square inch would probably be very painful. What I'm trying to say is that as humans, we're very fragile. I mean, even 10 pounds per square inch probably would be painful. And then let me amaze you by saying that the structures that we make, that we use in everyday life, they would, if they were sentient and they could talk to us, they would be laughing at us. They'd say we are so weak because they can handle tens or hundreds of thousands of psi. You see the difference? So the 590 psi for an everyday structure is a joke. It's nothing to it. It's nothing to it. It won't even break a sweat if it was sentient and it was alive, right? Anyway, so when you're designing structures, you want to consider how many psi's of stress that material can handle. It's not strictly about how much force it is or how much area you have. It's the combination of the force and the area that dictates the effectiveness of the material and the setup. You can see an example here of visualizing a concrete pillar, and you can see the 590 pounds of force internally flowing through an area of 1 square inch. These units that I've presented here, psi, are in the imperial system. There are equivalent units in the metric system. So I'll go to my summary at the end here. And I don't know if I've documented it. There it is. So this will come in handy very much so in this chapter. This table here, again, I'll post this on Blackboard at the end of class. These are the units that you need to be very familiar with, everybody, okay? And that video that I recommended at the beginning of class goes through this in very diligent way. But here's the big thing: stress. Don't worry about the math. Don't worry about the symbol. Ignore the symbols right now. So the stress in the imperial system we just claimed or said was it's psi. Now the area and the force they have to be in square inches and pounds if you want to use PSI as the measure of stress. We haven't discussed the metric system, but it is an opportunity for me to just say it here. In the metric system, stress is given these units called megapascals or megapascals. Capital M here stands for mega, and many of you know probably that mega is a million. Mega means million in math. It's a prefix that is a substitute for 1 million. So the force units in the metric system will be newtons, and because we're using megapascals, it goes against your intuition of using square meters, because with metric system calculations, you've been trained possibly that meters squared is the base unit for area. But in this case, since we're using megapascals, the base unit of area that I prefer to use, and most people with these calculations, is square millimeters. So I just wanted to take a detour there and just discuss those different units. So this table here, to say it simply, you should have this table beside you during an assignment or a test or whatever, because it will be really useful in terms of what you need to know for quick calculations. In fact, these last 2 pages here that I'm giving you, pretty much a gift here. You can use that as part of your cheat sheet for your test. Now, when I say cheat sheet, your test is open book. As you know, I'm not here to police you about using your notes or whatever. The trade-off is it's not a 5-hour test. The test is an hour and a little bit, so that's all good. So, in other words, if you don't know what you're doing, you're going to run out of time. And most of you during the tests have been very, very effective at being prepared and using the notes to your advantage. Okay, now the next couple of pages, which are the different types of stress, are related are relayed to you. Sorry, I just have the window open. The truck was driving by. They're being relayed to you over the next 4 pages. So without getting into too much detail on tensile and compressive, I'll just mention a couple of things, and then I'll talk a lot about the shear, because the shear is the one that some of you mentioned in the chat that's not as common knowledge for people. So I already mentioned about lines of action. So remember that I mentioned here the lines of action coincide for tension. And that's also true for compression. See, for compression also, the lines of action must coincide. The thing that's interesting is, I'll just summarize it here in my own words. Tension is pulling, but what's going on the inside? So on the inside, internally, tension acts inward. See, that's a very counterintuitive thing to say to people, because you think of tension as something being pulled apart. But the thing is, inside, so when I say it acts inward, what I'm saying is on the inside, it's pulling back. It's pulling back like that. So that's a beautiful way to say it, Shalon. For tension, molecules are attempting to stay together. You know what? That is a beautiful way to say it. I'm going to immortalize your statement right now. Okay? I'm just going to put a comma in there. So, permission to copy you, Shalon. Permission to copyright this. Okay, here we go. So I am plagiarizing off of one of my lovely students here. Oh, come on, it won't let me paste. I was telling you something's up with PowerPoint. Oh, there we go. I might close and open PowerPoint after I finish my little conceptual discussion here. Don't mind my editing. I threw a comma in there. So that's basically the idea there. For compression, oh, you're hilarious. You're hilarious. I should cite this. I need to, but if I put your name here, then I'm disclosing your name publicly, and I don't want to do that either, out of respect. So anyway, for compression, we have it pushing outward. So it's pushing this way. So the material, like a spring, if you want, it's pushing back. So like when you get in your car or something and you get in the car, the springs in the car push down. Well, the springs are pushing back up at you because of the extra mass and the extra weight that you're applying to them. And can anybody state a very famous law from physics that explains all of the stuff that we've been chatting about on this page? So I'm going to state that right here. It's something from the previous booklet that I asked you to read on your own. For every action, how does it go? There is. Okay, Amira, you're close. There's one more word that I need from everybody. There's two words. There is an equal and op. Oh, A+ there. There you go. There you go, people. That's what I'm talking about. For every action, there is an equal and opposite reaction. And who is this statement attributed to? So which law is this? It's okay, Amira. All due respect. This is Newton. Yes, it's Newton's third law. Just wanted to fix that dash there. There we go. So that's the principle, the physical explanation as to why these different reactions are occurring. So let's talk about shear. So there's a diagram on the next page which you can read on your own, which is just some examples to play with. That's page 6. So I'm going to skip that and I'm going to go right to shear. So here's the idea of shear. It's coming up. It's on page 8. There it is. There we go. Okay, I have an interesting thing for you to look up historically. It's a movie. Who's seen The Karate Kid? Who's seen The Karate Kid? This is very important, people. Very important from explanation. Who's seen the original, the OG Karate Kid, the first one from the 80s? Okay, I need more than 2 people, otherwise my explanation is going to be garbage. Anybody else seen it? Anybody else seen it other than Danny and Shalon? The original one. Okay, so your homework is to go and watch the original Karate Kid. Okay, anyway, what I want you to do, yes, I want you to do the following. Take your two hands and put them together, kind of like you're praying, you know. Maybe I can't put my camera on because it's going to slow down the recording. But imagine rubbing your hands together. Try to rub your hands together. Just lightly, okay? Lightly. It's pretty easy to do, isn't it? It's kind of smooth, you know. Maybe you have the nice manicured hands or whatever. Now, push your hands together really hard so that nobody can separate your hands. And try to rub them together now. Do they move anymore? Do they slide against each other anymore? No. So, what you've done right now with your hands is demonstrated the concept of vertical shear stress. Vertical shear stress. See that? What your hands did by changing the amount of rubbing against each other is you altered how much vertical shear stress you are imparting on your hands. The more vertical shear stress, the stronger the connection between them. But also there's a penalty possibly that if you go too far, you might hurt yourself. Well, there's something of an analogy in terms of a beam. And it also explains how the force is transmitted. So this will explain a little bit more about shear. Here's a line of action for these two forces, and of course there's a third force there. Now, forget about this force on the side. What I want to explain to you now is how this thing here and this thing here, how those forces eventually somehow connect to each other. And what it is exactly what I was describing. See these pairs of arrows here? See those pairs of forces? You see, I know they're really small to see them, but you see them there in the chat? Those two arrows that are those two arrows are like your hands rubbing on each other. That's what those are. So what's happening is adjacent molecules are rubbing on each other vertically, and that effect is going through the beam sideways. Can't draw the arrow there. It's going through the beam sideways. So that rubbing effect vertically is called vertical shear stress. And that's how this 1,000-pound force connects to the 500-pound force, and for that one as well, due to symmetry. Let me give you a material, a structure, if you prefer, that is really, really, really garbage at shear stress, at vertical shear stress. Ready? Here's the worst structure that I can think of for vertical shear stress. And if you have a deck of cards, you can do this later. Take a deck of cards, and this time put the deck of cards between your hands, and try to push as much as you can. And then if you have someone else there with you, try to let them pull your hand down. Do you think it'll be easy for them to pull your hand down when your hands are compressing this deck of cards? What do you think? Of course, because that deck of cards is going to slide so fast. So what you've just designed is the absolute worst structure ever for shear stress that I can think of. In terms of materials, some materials are more susceptible to vertical shear stress, whereas other materials are more susceptible to horizontal shear stress. So literally the word horizontal just means that this rubbing, if you want, this sliding, is sideways. So in this case, horizontal shear stress, there's two materials that I can think of, which are wood, and I'll just say here CF because I can't fit the words in there, carbon fiber. Think of carbon, carbon fiber, they make like auto parts with it, and they make like other very, very high-end and expensive materials. Yeah, for lightweight and for definitely for performance, of course. So wood and carbon fiber, the reason that they're susceptible to horizontal shear stress is because they are either designed or naturally occur in layers. When materials occur in layers, horizontal shear stress is the issue. When material is more of a bulk quantity, like steel is like more uniform. There's no layers. Nobody says that steel is layers. That doesn't make any sense because steel is melted and formed in terms of what we do with structures. So anyway, vertical shear stress will result in catastrophic failure where eventually it'll fracture and the material will literally just break off. No different than, unfortunately, if someone breaks their arm or something, very similar to that. Now, in terms of horizontal shear stress, the layers will separate. And what's holding the layers together is either a natural or a synthetic type of glue. Now, in wood, it's a natural type of resin that keeps the layers together, and in carbon fiber, it's some type of an epoxy or some type of a more sophisticated adhesive that holds it together. So I try to do it in half an hour. It looks like I've been rambling on here quite a bit, but we're getting there. We're getting there. I want to do 2 more pages, and I think that at that point we start to shift our attention to mathematics. So there are a few definitions here. There's the ultimate stress. Sorry, I don't want to highlight them. I'll just bar them like that. Ultimate stress, elastic limit, and allowable stress. So these are 3 quantities that depend on the material that you're working with. So not every material like steel or copper or concrete or whatever the heck it is, they're not all designed equally. And not saying one's better than the other, because of course in design, it's not just about which is the strongest or most versatile, it's also about cost, it's about implementation, it's about a lot of things. Like it would be very expensive to make a bridge out of carbon fiber. but I could make some really cool shapes out of carbon fiber. Anyway, there are numerical values which you need to be aware of to use to do questions. You don't have to memorize any of these numbers. I just want to direct your attention to them. But first, let's define ultimate, elastic, and allowable stress. So ultimate stress, the word ultimate does have that, zenith or pinnacle amount. That is the most stress that a material can take. So ultimate is basically the bottom line, is the maximum that you could put on a material. The ultimate, like on a car, like a race car, it's the red line. After that, the engine fails. The transmission or the engine. The elastic limit is the limit of stress that once you remove it, it'll bounce back. Okay, it'll go back to its original shape. So elastic limit is about preserving the integrity and going back to your original shape. So for example, you would want to make sure that anything that you design is definitely under the elastic limit, because you want it to bounce back to its original shape. Like a bridge, yeah, let's say that a convoy of vehicles goes across a bridge, but once those vehicles have passed the span of the bridge, you want the bridge to return back to the original shape. You don't want it to just not break. This is what ultimate says. It didn't break or fail. Now, allowable stress is the practical number. This is the number that you use in design. So allowable stress is based on building code. So allowable stress is basically think of it like the law, okay? It's the legal amount, if you want. It's what you should design for or design under. For example, I'll give you an example, a very simple one. Let's say that you have a race car. The race car can do 260 kilometers an hour. That's ultimate. If you go to 260, you might damage the engine. But let's say that you only take it to 200. That's elastic limit, meaning I can take it to 200, but then when I go back to zero, the engine's just the way it started. It's not damaged in any way. It's like it never happened. Allowable stress is the speed limit, which is 100. Let's say you're on the 400. Okay, so allowable stress is the speed limit. It is the regulated amount, the amount that you should design for. You shouldn't pass that number for safety reasons and other reasons, of course. So primarily those safety, and secondary, of course, legal. So in this case, you'll see that there's a table on page 10. And after I present this table and discuss it a little bit, I think we can take a short break. And then after the break, we'll come back and do some calculations. Perhaps I can introduce the formula for stress as well before the break. I really want, once we finish this first hour, to switch to application and numerical calculations. So look at this table in some detail, and we have the following quantities. So you'll have a much clearer diagram in your notes, but we have here the elastic limit and the ultimate stress, and this is for 6 materials. First thing I want to point out is that notice that we have steel here, and there's different types of steel. Now, this is a very simplified table. There are hundreds of types of steel, as are other permutations of these metals and possibly metal alloys. The main thing I want you to take out of the table is that you know how to interpret it, okay? So, for example, if we did the elastic limit of aluminum in the metric system, this is the number that you put together. So can someone tell me what that number is in expanded form? Because I see 1.3 here, but is it 1.3? Is it 1.3 or what's the final number? Type it in the chat. What do these numbers in yellow ultimately, what would you say? For the elastic limit of aluminum in the metric system. I'm going to help you out in the chat here. It's 130. 130 megapascals, okay? I'm typing it in the chat. Let me know if that makes sense to you. Let me know if that makes sense there, people. Anybody else? I got one person so far. There's 16 students here. I'd like to hear from more people. Anybody else? Thank you, Amira. It's so quiet. What happened to everybody else? Okay, well, you're gonna tell me right now. I'm gonna erase these guys here, and I'm not leaving this lesson until I want 10 people in the chat to tell me the answer to this one. I'm gonna type it over here, okay? In expanded form. I want the ultimate stress for brass, Imperial. All right, talk to me, people. Ultimate stress, brass, Imperial. Go. That's excellent, Shalon. That's excellent work there. So, that's 2 people. Maha, yes. I got 3 people. So, I was asking for 10. I'm not setting the bar too high here, hopefully. Here's ultimate stress. Here's brass. Thank you, Denny. George, there we go. Now we got half a party here. We got 5 people going. And 6.7, because it's in the Imperial system. And I like how people are writing the units there. So I will do the same. Amira, it's in the, I asked for the Imperial system. You gave the metric system. So to be clear, this one's the metric one, and this one's the Imperial one. So your number, no, there's nothing wrong. It's all good. Better to clear, you know what the best part is? It's better to clarify it now so that it's not an issue. So it's good. So the final answer is 67,000. So we'll have your 6.7 times 10,000, because 10 to the 4 is 10,000. Now, where it says LB per square inch or pounds per square inch, I'm just going to write PSI. So final answer, 67,000 PSI. Okay, so that's one, right? One more. Let's do iron, elastic limit, metric. Okay, go. Final answer. Once I see 7 answers, I'll put the answer up. Got 4 people. I want 3 more answers, please. I want 3 more unique answers from individual entities. Nice try, Shalon. All right, Julio, welcome to the party, my friend. Okay, 2 more. Otherwise, I'm gonna really drag it out here. I'll keep you in class till 5 o'clock. Don't worry. You don't know me well enough. I'm gonna do a math filibuster. Keep you in here all the day. All right. 160 is correct, but I was very disappointed that only Maha presented the correct answer, because Maha put the units down too. Sorry. So all of you put the correct number, but don't forget those units. Okay? All right, one more. Hopefully don't think I'm a jerk. I'm trying not to be a jerk here. I'm trying to be helpful. Okay, hardened steel. Spelled correctly, hopefully. Stel. Can't spell, eh? Hardened steel. Ultimate. Metric. Go. I'll leave this one up for the presentation as I post it on thing. Okay. All right. And everybody had the correct answer, but this time I'm going to be a massive, massive jerk. So here's why I'm a massive jerk. Because when you write the units for megapascal, make sure you capitalize the letter correctly. MP, lower a, okay? Because it's capital M for mega, and then it's PA for a physicist named Pascal, Blaise Pascal. Sorry, you know what? You probably hate my guts because I'm trying to like, kind of like hold your hand through the process. But the thing is that, look, if your professor's getting cheesed about if you capitalize a letter, no, yeah. If your professor's getting cheesed about you capitalizing a letter, if that's the only flaw that I can find in your work, then you're doing really well. Because if you weren't doing well, I would never bother you about capitalizing a letter. Like if a student's failing horribly, I'm not going to go and sit there and complain to them, oh, you didn't make the M a capital. Imagine that, right? So you are in a very good place right now. So, but the thing is that if you're really good, because you're typing in the chat, all of you so far, and you're typing really smart things, the only thing that I want to do is raise the bar higher and challenge you to be at a higher level of excellence. So that's good news, people. We're going to take a break in a minute. What I want you to do is just take a look at this is on page 11. And if you want, you don't have to read this during the break. If you can't read the size of the slide here, these notes are on Blackboard, so make sure that you do access those notes. But we will take a break until let's see here, 10 for 9. We'll take a break until 11:05. Okay, break until 11:05. Good work, everybody. I'm gonna step away from my computer. I gotta go do a few things. Well, that's what I'm saying. You can read it if you want, or not read it, but it's a fake break. Fake break. We'll discuss it after the break for sure, though. And make sure that if you have time, go watch the other video that I suggested, because it's a very useful thing to watch, as it'll do what we're gonna do in the second hour. I covered in that other video in detail as well. So it's kind of like extra practice. Okay, I'll be back in 15 minutes. Moving on now, we're going to talk about formulas. So this is the key formula for the unit, which is stress, and then P is force, and then A is area. The symbol here, hello? Sorry, I think someone's mic was on. So this symbol here is the Greek letter sigma. So you can write it looks like a whistle. You can write it like a lot of people write like a 6. That's fine. I'm not going to pick on anybody, even though I speak and write Greek fluently and am essentially qualified to teach it even. So there you go. That's the formula for stress. In terms of the units, let's put the units aside for a second, because as you saw me drawing in the break there, I'm going to show you those triangles to help you remember everything. So I'm going to do that right now. So here's some triangles that will help you remember how to write down and use the formula. So I've written it 4 ways. The first way is just with words. The second way is with the symbols. And then most importantly, it's these guys down here. Here I've written the formula in terms of the metric and the imperial system. So you can see that the consistency with the units is very important. Whether you have newtons, megapascal, and millimeters squared, or you have pounds per square inch, which literally tells you pounds per square inch. At this point, we are in a position where we can do questions and calculations. I will mention that there are some key things to talk about in terms of design. And I'll just flag this one last formula. Don't worry about this formula for now. It'll pop up in examples next week. And this formula too. This will pop up next week's class, okay? But it's important to say that when you are doing design, maybe that's too dark. Let me go with a yellow maybe here. That when you want to talk about actual application, make sure that you design something safely this formula is going to come in handy, which involves something called a factor of safety. So anyway, this is what we'll do for the rest of today's class and moving on to next week. You can see here that there's about 6 or 7 key examples, and I'll just scroll to the top of these pages. My advice to you is to look through these examples as they do have complete solutions. We have example 1, 2, 3, 4, 5, and then boom, we have exercises. So what we're going to do now is focus on computing, doing calculations practically with stress. For testing purposes and for the examples that I'm showing you for the remainder of this chapter, we are not going to do shear stress calculations in this course. So say that again, there are no shear calculations in this course, only tension and compression. And in that regard, tension and compression results basically are the same steps. You just need to relate the applied force, the cross-sectional area, and the stress. So now that we have ourselves organized here, just take a moment and read this example, and we'll start to set up the answer together. So this is example 1, and I don't know how far we're going to get. I haven't planned that in advance. I want to see how you do and respond to the material. Usually I do that every year, however fast we go or however slow we go, it doesn't matter. We have our goals and we'll reach them. So you're reading through the question there. The dimensions are presented in the diagram. It's hard to read them possibly, but you can see them in the main text here. It's the same quantities. So if you can't read this number here, that's 2 1/4 inches, and that's 1 1/2 inches. So it says here to compute the compressive stress that's occurring in the block. What will be of benefit to you is having the formula here on the side maybe. Let's go there. This stuff here, okay? So I'm going to put that on the side right here so that you have it at your disposal. Hopefully that's large enough to read. So we're asked to find the stress. So based on this triangle here, you can write down the formula for the stress. Stress is equal to force divided by area. That's literally how the setup is. So let's write that here. Stress equals force over area. Do we know the force? What's the force? Anybody know the force from the diagram? Yeah, it's 8360. Now, for these questions, I encourage everybody to write down units. So 8360 pounds. The thing is, the pounds indicate that the question is in the imperial system. I promise not to give you a question that has a mixture of metric and imperial calculations. So if the question's imperial somewhere, the whole question's imperial. If the question is metric somewhere, then the whole question is metric. So no games, okay? No conversions of that crazy stuff. Now, the area, which area is it? So this is the part where you have to look at the diagram. The area refers to the area over which this force is distributed. So some people might think it's the surface area, and it's not. And thank you, it is the top. Actually, further to that comment, Shalon, it's the top or any cross section in between. Any of those slices. Any of those slices that act perpendicular to the force are representative of what the area is. So in this case, the area, we anticipate, I'm just cutting out a step there. I will fill in these steps in a second. I promise to fill these steps in a second. We expect an area in square inches. Oops. We expect an area in square inches. So that means over here, you want to write down the length times the width, since the shape is a rectangular prism. So what I'm saying is, there are numbers possibly in the question that you shouldn't use. Like some people, oblivious to the physics, will just say, oh, I'm going to find the volume because I have three numbers. And when you multiply three numbers, you get volume. But we don't want volume here. We want cross-sectional area. So the length and the width are which numbers? Can someone tell me which number of these three numbers is garbage? Which one do we throw away? Yeah, this number here we don't care about. Good. So the numbers that we really want to retain here are the 2 1/4 and the 1 1/2 inches, respectively. So let's do that here. So 2 1/4. I expect you to know your fractions. I'm not worried about that. The book says 3 significant digits. So although I don't explicitly, that's okay, Ram. As long as you know the assignment is due today. I don't know if you've handed it in already. That's all. That's fine. So notice that when you multiply that out, you get a value in inches here, square inches, sorry, and you can round that. So again, if I don't tell you, everybody, it's in the booklet. It says 3 significant digits. So I got 2480 psi. Awesome. Now some people will say, why is it psi? Because the units are consistent, but I can clarify that by just writing an extra line of writing. Hopefully just make life a little bit easier for people. Remember, pounds per square inch. There's a little bit of a delay here, sorry. Pounds per square inch literally means psi. How did you feel about that calculation? How did you feel about that calculation, people? If you found this one, that's good news. That's good news. Thank you, Amira. Thank you, Shalon. If you found this calculation pretty easy, that's good because that's what it's supposed to be. This is like the opening question. And that video that I recommended you to watch does stuff like this as well. By the way, if you're wondering, are we going to do any design kind of thing here? Well, of course, this is a first-year course, so the course outcomes are not to the extent of designing something profound, but you will be able to investigate something some very realistic calculations, especially in some of the upcoming exercises. So moving on to example 2, exercise number 2. I just have to click on it and come back. And I think we're good. I'm trying to keep this triangle on the side here. There we go. So an iron cylinder, oh sorry, just read the question on your own, that's fine. So I'm just kind of getting a head start on the discussion here. So that 2200 kilogram mass that is pulling down is going to pull the iron bar and put it into tension. You might be wondering, like, if it's pulling down here, is it just going to fall? Why doesn't it fall? Because there's a contact force to the ceiling. In other words, there's an equal and opposite force on the ceiling that's pulling it up. So that's the reason that it's in equilibrium. It's not going to go anywhere. The thing is that we are in the metric system. This is a metric calculation. So we need to convert this, convert kilograms to newtons. That's what we did in the previous booklet. So I'll just do the calculation here. 2200 kilograms. Remember we did 9.81? It's the weight of the object. If you're like, I don't understand this step here, you need to review the previous booklet a little bit because we did it there. And when you do that, you get 21,582 newtons. Now, I'm not asking you too much for calculations for the sake of efficiency. Exactly, you're multiplying it by G. You're multiplying by G. This number here, this quantity here is G. This purple number here is G. And so that is the acceleration or gravitational field of the Earth. Of course, if this iron bar was suspended from a ceiling in the following situation, and you were on the moon, then that purple quantity, 9.81, would be a different number. So that's anyway the force. So we're going to actually put the letter P here, the variable P, because that represents the load or the force that's pulling. Now we need the area. So the area is a circle. You know circles because you absolutely rocked on your second test. When I asked you about spheres and all kinds of weird stuff there, I didn't really see too much challenge there. So I'm going to ask you to tell me, what do I put here? What number do I put there in the bracket? This one's dangerous. 1.91. Aha, you are good, but I want better. So look on the side here. See this triangle? We're going to call this the triangle of pain. That's the triangle of pain right there, okay? Now, that's millimeters squared. You see that? Millimeters squared? So Maha was correct in identifying the radius. See, the diameter is 3.82 centimeters, and the radius is what Maha stated, which is 1.91 centimeters. That's right. You're close, my friend. 1.91 centimeters. But we need to convert that to millimeters. So that's 19.1 millimeters. So this step here, yeah, we got to please be attentive to that. Yeah, this is the little stuff that kicks you in the butt, you know? This is the stuff that you're like, damn, I should have got perfect, but I forgot about something silly. So anyway, 19.1, I'm going to put the units here. You're going to find that I'm being very picky about writing units, but I'm only doing it to ensure that you respect the process and the importance of having these units. And look at the answer here. Isn't that cute? It's our course code. How cool is that? I think that's pretty cool. We're going to call this the course code question. Whoops. All right, good. So now that we have that, we can answer part A. So here comes part A. See, that stuff that we did there, it's insensitive to part A or part B. That's just information that you can take from the question and kind of play jazz and do whatever you want. But now we're going to kind of tie things together to answering the question. The first question says here, let's see here, calculate the stress. So I'm just going to highlight the key phrase here, tensile stress. And then the second thing is the percent of the elastic limit. We'll come to that later, don't worry. But let's just talk about the stress. So stress is equal to force over area. Force we're given, oh, we just, honestly, isn't this cool? We just copy and paste a bunch of stuff, see? Now, you don't have that luxury. You have to write this by hand. Unless you're typing this. Some of you do like to type things for your assignments, which is cool. I like that. But I'm not going to frown on it if you don't type it. Oops, let's go here. One thing about typing with the video being recorded, there is always a lag. So I feel like I'm typing 3 steps ahead in the computer, and what I see and what I write, it's not synchronous. Anyway, I got 18.8 megapascal. So the question here is, what percent of the elastic limit is reached? So this is just about calculating a score. So for part B, well, what material is it? Let's take a look. It's iron. It's iron, okay? For the sake of me not going back and forth, you remember before the break I was asking you to read the table a bunch of times? Well, I'm not going to get to read, I'm not reading the table right now. We have the elastic limit of iron. So this is sigma for iron, elastic. Can someone go to that table if they have the notes with them? Oh, very good, Shalon. So it's 160 megapascal. Now I do feel a little bit like I'm letting you down there. So let me go back to that table. Elastic limit of iron, metric. Here we go. Here's the table. Elastic limit, iron, metric. The number is 1.6. See where my cursor is, the cross there? It's 1.6 times 10 to the 2. So 160. 160. So this question is obviously more writing than the previous one. But that's how these exercises are. It's a short question, then a long question, etc. So the final answer here, here's my answer. It's going to be 18.8 megapascal divided by 160. I don't care if you, some people do this. This thing, you don't have to write times 100. I'll write it there, but you don't have to write that. Anyway, 12%, okay? So I got 12. Can someone confirm 12? Thank you, Shalon. Oh, no, it's okay. All right, so you're kind of getting the sense of how this game is going to play out now for the rest of the lesson. So my goal with you, I'm just going to skip ahead. I'm just kind of reading ahead in my own personal notes here for a second. 17, 18, 19, 20. So there's 20 questions. We did 2 of them. And I don't see why we can't do all 20 of them over the next 20 minutes plus next week. So once we finish these 20 questions, the course is done and you can focus your attention on the final test. So I'm just going to try to hammer out maybe a couple more with you, and then that's it, okay? So 2 more questions perhaps, and then we can call it a day. This one was a longer one, obviously. Perhaps the next one isn't too dangerous. So there you go. Take some time to read it. I'll start answering it in a few minutes. In about 30 seconds. Okay. So I mentioned earlier, remember I said to you there was a diagram for exercise 1, and I said which number is useless? Which number is useless in this question? Which number do we not really care about? The 7.2, yeah, this number here. Now, I want to clarify that because there are people that are going to watch this later, the recorded version, and say, wait a second, sir, 7 feet 2 inches is important in real life. And I should just clarify, for the purposes of stress calculations, that 7 feet 2 inches doesn't matter. However, in real life, the 7 feet 2 inches does matter for other reasons, okay? And the reason is this. This yellow quantity here, it affects something called buckling. I'll type that in the chat. Buckling. Ever heard of buckling? In the chat, let me know. Anybody heard of buckling? So what's buckling? Someone type it in the chat. Type out their own, like, shaking, okay, what I want you to do, okay, imagine this, buckling. I'm typing it again. I want you to imagine a piece of pasta, okay? Let's take a piece of spaghetti. Here's a piece of spaghetti, okay? Now, if I push on it here, what's going to happen to it? What's going to happen to the spaghetti if I push on it? It's going to do this. It's going to form an S shape and it's going to snap. That's buckling, okay? Buckling will occur way before it gets compressed, because even if you had the most perfect arrangement, it would still buckle before it would fail by the compression. Like, for example, you know that if you take a piece of pasta, or at least you should try this as an experiment, safely of course, with safety glasses and all that. If you take a piece of pasta and you pull on it, it's pretty strong. It's pretty stiff. The word is stiff. Stiff meaning it can resist a lot of stress. So that's the idea, that even though it can resist a lot of stress, the aspect ratio, that is the height to the area of the cross section, that ratio plays a role. Buckling is really, really important, but of course, if you're looking at this column here, it's 2 feet 10 inches wide at its cross section, so it's pretty safe to say it's not going to buckle. So if the column was only 2 inches wide, I would assume it would buckle before it would fail under compression. So enough talking about buckling. You're not going to be tested on buckling in this course. That is much more advanced engineering topic. But anyway, let's do some calculations, people. So we have the force. So the force is equal to 56 tons. We'll talk about that in a second. And the area is of a circle, which I'll write here, pi r squared. And then we eventually get the stress. So that's what we're working with. But now it's up to you. Well, it's up to all of us, I guess. It's up to all of us to figure out if we need to do extra work here, because there's information that kind of looks a little bit fuzzy. I'm not really satisfied with a few things here. So first of all, if you look here, is this question in the metric or the imperial system? Let me know in the chat. Is this question metric or imperial? Imperial is correct. And the clue was the feet and inches, also the tons. Does anybody remember how to convert tons to pounds? Because we don't want tons, we want pounds. How do you go from tons to pounds? What's the conversion? How many pounds are in a ton? What's the number that goes up here? How many pounds are in a ton? Correct. 2,000 pounds in a ton. So if we do 56 times 2,000, you can do this in your head. 56 times 2 is 112. Toss in a few zeros for the 1,000, and you're good to go. Also the area. Now this one's dangerous because the area requires the radius. The radius is not 2 feet 10 inches. It's 1 foot 5 inches. Do you see that? This one was easy to do in my head because they're both even numbers. Like, you could convert that to inches if you want first, and then divide by 2. I just kind of did it lazy because they're both even numbers. So 1 foot 5 is 17 inches. So we have the goods here. So that's pi, 17 inches squared. The reason that I wanted inches is because my triangle here with the units, the base units for stress calculations in the imperial system are inches. So if we type all that out on our calculator, whoops, I did this earlier to save you a little bit of pauses. The last thing you want me to do is type on the calculator and waste. If I typed every question on calculator in class, we probably lose 5 minutes of lesson just on that. Think about that, eh? Me punching numbers on the calculator wastes about 5 minutes of class. I've done it. I've actually timed it. I've timed it for a 2-hour lesson because I was curious one time. Well, I don't want to toot any horns here or whatever, but I was actually talking to a friend of mine on the phone yesterday, and they're like, "Oh, what's this 3-digit number times that 3-digit number? Can you do it in your head?" I'm like, I don't want to do that in my head. I want to go out for a walk and enjoy the nice spring weather. I know we're under advisory to stay at home. But obviously, for exercise reasons, I do go out for my walks in the evening when nobody's around. And yeah, it was a beautiful night last night. I don't know about you guys if you got a chance to get some fresh air last night, but it was gorgeous out there. Anyway, I got 123 psi. That number there, if you're wondering for the design perspective, thank you. From the design perspective, what does that mean? I'm not asking you to take that number and talk about its practical, like what it means practically. I'm just focusing on really just the formula calculation for this question. But I promise you we will talk about the practical effect, and that's where factors of safety come in, which was what I was referring to briefly as we started the second hour. Just excuse me for a second as I fix something on my computer. Thank you. Sorry, everybody. I'm just trying to open up a file, and it's not letting me adjust the file. Okay, here we go. Next question, number 4. How's everybody doing? Do you have class after this? Who has class after this? What time is your class, people? Okay. So, okay, I gotcha. So you do know, maybe we'll make this the last question. My goal was to get to 4, so that's good. Um, just keep in mind, next week we're going to try to hammer out as many questions as possible, and then the last week of class, there's no class, it's just a test. So I'm trying to get everybody packaged and ready, all the dots, all the I's dotted, all the T's crossed. I want everything done by next Friday so that I can wash my hands and you can wash your hands of this and just say I have to write a test. That's it. I will also try to post your 11th assignment, which is I usually post on the Sunday, Monday. I'm going to try to post it sooner so that you can get that out of the way if you want, just for your own preference, if you want to just move it along as well. All right, so last question for today's lesson here. We have the maximum weight that a copper wire can support without becoming permanently deformed. So, all right, let's get some of the easy stuff out of the way. Let's say you're writing a test, right? And you're looking at this and you're like, I don't know where to start. Well, the first thing that I would do is the easy stuff. For example, the radius is a quarter divided by 2, which is 1/8 of an inch. That's the first thing that I would do. Then the second thing I would do is get the area. Like, do the stuff that's easy. If you don't mind, I'm just going to put the final answer for the area. The final answer for the 3 significant digits is 0.491 square inches. Like, do the easy stuff. Nobody's gonna laugh at you or make fun of you. Like, I would do that. I would totally do that. Like, why not, right? Get something in your pocket, get something in the bank that's easy. Now the question is, we want to find the maximum weight. So continuing on this thought process, so we have the geometry out of the way. Now we're going to talk about the force. So the force is unknown. That's what we're trying to find. But the question is, what the heck is the stress? So this is where the table comes in handy, where we investigate the material property. So what type of material is this? Let's get to that in a second, Shalon. Sorry, one step at a time. What type of material is this, people? Can you help me out here? What type of material? Copper. Okay, someone else. Are we in the metric or the imperial system? Someone else. Thank you, Shalon, but someone else. I need more people. Imperial, okay. One last thing. Not becoming permanently deformed. Not becoming permanently deformed is elastic, okay? I can spell. Elastic. Okay? So that's huge. That about permanent deformation. So the number that Shalon reported, I'm assuming, was the ultimate value. Is that correct, Shalon? You found the ultimate value? Good. But we're going to use it's okay. We're going to use the elastic value. So from the table, that's 22,000 psi. What page is the table on? Can you tell me from the notes so I don't have to slide through it? So what page number was that? It was page 5, isn't it? Or no, sorry. My bad. I'm not being lazy. I'm just trying to not waste time on that. Thank you, page 10. From the notes, page 10, okay? From the table. On page 10, 22,000 psi. So there you have it, my friends. Toss in the triangle here. So we're trying to solve for P. So P, if you look at this triangle, you multiply stress times area. So we have all the goods in place here. We have 22,000 psi. we have the area, which is 0.0491 inches squared, what the heck happened there? There we go. And if we round that to sig figs, 3 sig figs, I got 1,080. Can someone confirm? Anybody else get 1,080? Sweet. Sweet. I think that question went by fairly quickly, but I maybe if you don't mind, I'm gonna do one more question actually. Okay, I will do one more question because it's basically the same thing, but this time it's braking. It's the same thing, but braking. So what number changes in the question? So remember that number that Shalon reported? It's basically the same question, people. That's why I'm doing it. It's like 2 for 1. We got 2 for 1 here. It's like buying pizza slices or something, okay? So not braking. Not braking, sorry. So this will become ultimate. There we go. So that one was the one that you mentioned earlier, which is 49,000 from the table. And that takes us to 2,410 pounds. And this is a good place to stop our lesson because it leaves us with kind of it leaves us on the precipice of something interesting. See, the material can handle 1,080. I can't solve assignment 10 question 4 because it's due today. It hasn't even been due yet. Malik, it's due today. I can't answer the question. It's part of the assignment. Sorry. That brings us into a comparison that I want to make here, which is that 1,080 pounds, that's how much the copper wire can handle and bounce back. And it can handle more than double that and not break. But what about design? What about real life? You don't want this wire to hold more than 1,000 pounds. In fact, you don't want to hold more than 200 pounds or maybe 300 pounds. So there's always a lower value, a lower threshold that you want to use, and that thing is called a factor of safety. So we apply something called the factor of safety, which says, although we could handle this much, we're not going to handle this much. We're going to divide it by a certain factor so that it's safer overall. So with that, I am going to conclude the recording and wish you all a lovely weekend.